All right, let's dive right in. Today, we are talking about something I can pretty much guarantee you've seen happen, probably right in your own kitchen.
So picture this. You're making a glass of iced tea, maybe some coffee. You add a spoonful of sugar, you stir, and poof, it's gone. You add another, same thing. But then you add one more and nothing. It just sits at the bottom in a sad little pile, no matter how much you stir. There's a limit, right? So what's the deal with that?
Well, that natural limit actually has a scientific name: solubility. You can think of it as the absolute saturation point. It's the maximum amount of one substance, we call that the solute, like our sugar, that can possibly dissolve into another substance, the solvent, like your tea, under a very specific set of conditions. So, as long as you can keep dissolving more sugar, your drink is what's called an unsaturated solution. It still has room. But the second you hit that wall, when no more sugar will dissolve, you've created a saturated solution. It is completely 100% full.
Now, this is where chemistry gets really cool. Because, sometimes it just loves to break its own rules. Saturated sounds like the end of the line, right? But what if I told you there's another state, a weird, unstable state that goes beyond full? And that is called a supersaturated solution. It's a solution that is somehow holding more dissolved stuff than it's supposed to be able to. It's totally unstable, kind of like a Jenga tower that has one too many blocks pulled out. It's just waiting for the slightest nudge to make it all come crashing down.
Okay, so this is where things start to get a little crazy, because the principles of solubility become incredibly important and honestly, even dangerous when we're not talking about sugar anymore. Now we're talking about gases dissolved in liquids. And for gases, the master variable is pressure.
This whole concept is governed by a fundamental rule called Henry's law. Now that sounds fancy, but what does it really mean? It's simple. The more pressure you apply to a gas over a liquid, the more of that gas you can force to dissolve into the liquid. High pressure means high solubility. That's it.
And the perfect everyday example of this is a can of soda. First, the factory uses super high pressure to force a ton of carbon dioxide gas into the flavored water. As long as that can is sealed, it's a stable, saturated solution. But you know that psst sound when you crack it open? That's the sound of you releasing all that pressure. Instantly, the liquid can't hold all that gas anymore. It becomes supersaturated, and all that extra CO2 makes a run for it, escaping as bubbles. Your soda literally goes from saturated to supersaturated in a split second. Okay, now let's take that exact same principle, but apply it to a much more high-stakes situation. A scuba diver's own body deep underwater. See, when a diver is deep underwater, the immense pressure forces more nitrogen gas from the air they're breathing to dissolve into their bloodstream. Just like the CO2 in that sealed soda can, their blood becomes saturated with nitrogen gas at that high pressure. But what happens if they come up too fast? Well, just like opening the can, the pressure drops fast. Their blood suddenly becomes supersaturated with nitrogen, and all that gas needs to get out. But instead of a harmless fizz, it forms dangerous gas bubbles inside their blood vessels and tissues. This is decompression sickness, famously known as the bends. These bubbles can block blood flow, causing excruciating joint pain, paralysis, or even death. This is exactly why divers have to ascend slowly, with safety stops, to let that gas escape their bodies gradually and safely.
So pressure is obviously a huge factor, but it's not the only game in town. Let's switch gears to another critical piece of this puzzle: temperature, and how it can affect an entire ecosystem.
Now here's something that might seem a little backwards. For most solids, like sugar, adding heat helps them dissolve faster, right? Well, for gases, it's the complete opposite. When you heat up a liquid, it can actually hold less dissolved gas. Hot water is terrible at holding on to gases compared to cold water.
And this has massive real-world consequences. Just take a look at this chart showing the amount of dissolved oxygen in water at different temperatures. See that trend? As the temperature goes up, the amount of oxygen the water can hold just plummet. So let's put that in perspective. A healthy freshwater trout, for example, needs water that has at least 7.5 milligrams of oxygen per liter. That's its survival baseline.
But let's say a factory dumps warm water into the stream. That's called thermal pollution, and it raises the water temperature to about 30 degrees Celsius. Suddenly, the maximum oxygen the water can hold drops to just 6.4 milligrams per liter. It's now below the threshold for the trout to even survive. The fish are literally suffocating.
All right, for our final story, we're going to look at a terrifying real-world catastrophe where all these concepts, pressure, temperature, and supersaturation, came together in the most devastating way possible. Back in 1986, at Lake Nyos in Cameroon, there was a hidden danger lurking. Deep at the bottom of this volcanic lake, CO2 was constantly seeping up from the Earth's crust. Now down there, the water is cold and the pressure is immense. This was the perfect combination to dissolve an unbelievable amount of CO2, saturating that bottom layer of water. Then, some kind of trigger, maybe a landslide, disrupted the lake, causing that deep, gas-rich water to surge to the surface. The pressure was gone in an instant. The entire lake became supersaturated and erupted, releasing a gigantic, invisible cloud of CO2. It was like the world's largest, deadliest soda can being opened all at once.
The result was just unimaginable. Because CO2 is heavier than air, that silent cloud rolled down into the nearby valleys, displacing all the oxygen and suffocating more than 1,700 people and thousands of animals in their sleep. It's just a horrifying, large-scale demonstration of Henry's law.
Isn't that incredible? The very same physical law that puts the fizz in your drink, when scaled up by nature, can become one of the most terrifying forces on the planet. It really makes you stop and think, what other hidden, fundamental laws of chemistry are quietly shaping everything around us, every single day?